In this video, we'll be looking at functions that blow up or blow down. We'll articulate a definition of infinite limit, give a calculus definition of vertical asymptotes, and formalize the notion of a limit existing. Let's first define a positive infinite limit. If the value f of x increases without bound as x approaches a from the left or the right, then we say that f of x goes to positive infinity as x approaches a from the left or the right. We write if x is approaching a from the left and if x is approaching a from the right. In the given graph, we see that as x approaches a from the right, the values of our function grow without bound. And we say that f goes towards or tends towards infinity. Now let's define a negative infinite limit. If the value f of x decreases without bound as x approaches a from the left or the right, then we say that f goes or tends to negative infinity as x approaches a from the left or the right. And we write if x is approaching a from the left and if x is approaching a from the right. In the graph, we see that as x approaches a from the left, the values of f of x decrease without bound. And we say that f goes or tends towards negative infinity. Next, I'll be making three observations. First, infinite limits are largely a one-sided affair. When dealing with infinite limits, you'll be asked whether f goes to positive or negative infinity. And since a function's limiting behavior can be different on either side of a, you'll invariably be computing one-sided limits. Here are graphs of functions that go to opposite infinities on either side of a. Here are graphs of functions that tend to positive infinity for the graph on the left, or negative infinity for the graph on the right, regardless of whether x approaches a from the left or right. In these graphs, the functions have an infinite limit on just one side of a, but a finite limit on the other side of a. This can happen, for example, with piecewise functions. Second comment, infinity is not a point on the number line. It's perhaps the elusive pot of gold at the end of the rainbow, the ever-receding horizon, the thing that's far and farther away, but whatever it is, it's not a point on the number line. So when we use the notation that the limit of the function is equal to infinity, that's perhaps consistent and convenient notation, but we're not saying that at the limit the function approaches a fixed point on the number line. Arguably, the arrow notation is more indicative than the equality notation of the behavior of a function with an infinite limit. This leads us to the third comment. When we write the limit of the function as plus or minus infinity as x approaches a, we're not saying the limit exists. It doesn't. For a limit to exist, the function has to be approaching a point on the number line. It's more like we're describing the function's limiting behavior and being more precise in what way the limit doesn't exist. Here's a matching problem. Take a pause and see if you can match the function with its graph. How well developed is your intuition about asymptotic behavior? Would you be able to explain your choices to a friend or classmate? Let's look at the solution. We'll be matching the functions to the graphs by looking at the infinite limits as x approaches a. If we evaluate these limits as x approaches 0, we always get something of the form a non-zero number divided by 0. A non-zero number divided by something that approaches 0 is always something that's going to go off to plus or minus infinity. Of course, this is a limiting process, so I'm putting the equality in quotes there. So how do we determine whether we get plus or minus infinity? Well, that depends on two things. C, the non-zero constant, whether it's positive or negative, and whether we're approaching 0 in the denominator from the positive side or the negative side. That, together with the fact that two positive or two negative factors gives us a positive result, or that if you have a positive and negative factor that gives us a negative result, gives us whether we get positive or negative infinity at the limit. For the function 1 over x, if we let x approach 0 from the left, at the limit we get a positive 1 divided by 0, where we're approaching 0 from the negative side, so positive divided by negative is a negative infinity. And as x approaches 0 from the right, we get positive 1 over a denominator that goes to 0, but is slightly positive, so that's positive infinity at the limit. You can work these out as an exercise if needed. Let's go back to the graphs and look at the answers. Now let's give a definition of vertical asymptote. Function f has a vertical asymptote x equals a if at least one of the following is true. And then we have four options listed where the two one-sided limits are either positive or negative infinity. All the graphs in this video so far have been graphs with a vertical asymptote, because in all those graphs, at least one of the one-sided limits was infinite. And because this definition of vertical asymptotes uses limits, this is very much a calculus-based definition. And let's see why this calculus definition is preferable or even necessary over a pre-calculus-based definition. The methods of pre-calculus wouldn't help us cope with functions like sine of x over x or sine of x over x squared, or allow us to differentiate between the two. But using limits, we can see that sine of x over x has a whole, and sine x over x squared has a vertical asymptote x equals 0. Using our special trig limit, we see that sine x over x does not have an infinite limit, therefore we don't have a vertical asymptote. Computing the limit of sine x over x squared as x approaches 0 from the left, we find that it's negative infinity. So since at least one of the one-sided limits is infinite, we have a vertical asymptote. We can also compute the limit of sine x over x squared as x approaches 0 from the right, and we get positive infinity. The numerator goes to 1 by our special trig limit. We see that the tools of pre-calculus weren't powerful enough to deal with such functions. Finally, let's be sure we are clear about what it means for a limit to exist as x approaches a. If the two one-sided limits are finite and equal to the same number L, then the limit of f as x approaches a is equal to that number L. So if the two one-sided limits are finite and equal, the limit exists, and we don't have to specify whether we're approaching a from the left or the right, because it doesn't matter. We'll do a graphical example and check whether the limit for this function exists at points a, b, c, d on the x-axis. To test for the limit existing, we'll use the criteria that the two one-sided limits must be finite and equal. At point A, since one of the one-sided limits is infinite, the limit in general doesn't exist. At point B, both one-sided limits are positive infinity, so even those agree in some sense, the one-sided limits are not finite, therefore the limit still doesn't exist. At point C, both one-sided limits are finite, but they're not equal, so again the limit doesn't exist. At point D, both one-sided limits are finite and are equal to the same number L. So we can conclude that the limit of f as x approaches d is equal to L without specifying from which direction we're approaching d, as it's unnecessary. Even though this video was somewhat conceptual, the next video consists of worked examples.